Welcome back. Today we're going to move on now to the anatomy of the kidneys, the ureters, and the bladder, which comprise the urinary excretory system. If you remember back to the colon had the functions of excretion, of some conservation of water, and then of convenience. We have the same in the urinary system. The urinary system is primarily one of excretion as well as an equal part conservation and then convenience for evacuation of the excreted materials. The urinary system is composed, as we can see here in the first slide, of the kidneys, the ureters, and the bladder. Here we have the paired organs, the kidneys, both sides. If you'll notice, the right is lower than the left. This is not accidental. This is because we have the huge liver filling up this portion of the abdomen and actually anatomically pushing the kidneys down lower on this side. The kidneys are supplied by only two vessels, which are what we call end vessels, the right and left renal vein, and then behind it, coming off the aorta, which you can't see very well except the upper edge, here is the left renal artery, and here you can see it peeking out below the vein on this side. There's no real collateral circulation here, but we do have a paired organ. So we can expend one of these organs if we had to, and nature did not have the necessity of having a backup blood supply to the organs themselves. Coming from the kidney is the ureter, and the ureter travels down the abdomen through the pelvis and into the bladder. Here it's obscured a little bit by the ovary, but it goes behind the ovaries, down low into the pelvis, and into the urinary bladder. It is an entirely retroperitoneal organ. Everything you see in this slide is behind the parietal peritoneum of the abdominal wall. The vena cava, the aorta, the kidneys, and all the way down to, but not including, in this case, the uterus, because as we remember, this is also where the rectum dives down to become a retroperitoneal organ. Also, the kidneys are not in the plane they're shown on that picture. They're not flat facing forward. Because of the mass of the spine and the musculature, the kidneys actually occupy this plane, not this plane. It has an importance in the protection that nature gave it. If we look at the next slide, this is a section that might be good to look at because it introduces you to the idea of a CAT scan or an MRI. In the section you see here, we've taken a slice horizontally through the body of the patient. Now, by convention or agreement, physicians have agreed to look at all of these the same way, whether we're looking at MRI, CAT scan, or anatomic sections such as these. It's in horizontally, we've taken a slice right through here. But then we've taken the top of the body and lifted up the bottom, so you are now looking at the bottom or looking up at the section, as if the patient is lying down with the head that way. If we come back here to this slide, what you'll see is this represents the anterior or the front of the abdomen, cut off a little bit because of the size of the slide. Here's the patient's back, and since we're looking up, this would be the left side, and this would be the right. Look now at some of the organs. You can get a nice idea of what we call relationships, something we emphasize in medical school and anatomy, but we haven't in this course. Here are the ribs. They're chopped off at angles because remember the ribs have a downward slope to them. So we would not cut between one or through one on a horizontal section. We'd be knocking off one after another, going from lower to higher since they're angled. Here are the muscles between the ribs. We talked about them, the intercostal muscles. And if we come around to the back, here are the big long muscles on either side of your spine. Here's the spinous process of the vertebra, the little knob you can feel as you run your fingers down your spine. Here's an empty space where the spinal cord would be. This is a drawing, remember. And here's that body of the spine. This one is level L2, just 2 down below the last rib, high in the chest. I'm sorry, high in the abdominal cavity. Then as we go laterally out here, we're looking at the left side. Remember, here's the spleen, and here's the pancreas. Remember how the pancreas ran? Now we've lost the top of the pancreas because it too runs at an angle, but it would end up in this plane right at the edge of the spleen. Still looking up, here's the stomach, the pylorus, and the duodenum, which would then sweep across below the level of our cut and then curve back up again to become visible here again. Here's a piece of colon on the left side traversing what we're looking at. And here's your vena cava. Here's the renal artery and vein going off to the kidney. A very nice orientation of the section. Of course, this big mass right here is the liver with its venous sinusoids and a few arteries. Now, we would see the same thing on a CAT scan or an MRI or even a PET scan, except they'd be in black and white. Now, here are the kidneys, and here's the intrusion of the spine, making the angle I just showed you. Here the kidneys have been cut across their midsection. In this one, we're catching the level of the artery and the vein. This side, we're seeing the vena cava in front and the artery coming behind. If you remember this picture, here is the vena cava and the artery coming behind it. So that was how we got to that on the cut. We also see the ureter coming out right about there, and it's at a different height than this kidney. This kidney is lower, so we've actually missed the ureter on that side. That's the anatomy of the kidney. The important point is that it is retroperitoneal and it has this end blood supply. It is a vital organ. You do need a kidney to survive unless we do something artificial like dialysis, which I hope to talk to you about later. The vitality is not so acute as it is in the rest of the body. Acute meaning a time frame. Acute means short time period, chronic means longer time period. For example, the brain has a window of opportunity of only a few seconds to minutes when it loses its vital function. The heart, 2 to 4 minutes. The kidneys, it's probably somewhere between 2 and 4 days. You can go without kidney function for a long time, several days, especially if you're careful about diet and fluid intake, but eventually it will catch up. And a patient who is on dialysis, the artificial kidney, usually doesn't start to feel so good just around the time they're due for another dialysis. And they usually go about 3 times a week. Just keep them in a nice, comfortable state. The function of the kidney, the primary function of the kidney, is to maintain homeostasis. It's there more than to just be an excretory organ, to get rid of wastes. It's there to maintain the balance. So what the kidneys do are they function to filter and get rid of wastes, dissolve particles, toxins, and to reabsorb water, important electrolytes, and parts of the buffering system. They're there to keep that balance. It's almost as if I sat you down in a garbage dump, and you're the kidney, and I started piling almost everything that I could find in the home into that garbage dump. That's basically the way the kidney does its work. It lets almost everything go out into the first part of this process. And then you would have to spend your time quickly sorting through and conserving the stuff we really need for our home, but getting rid of the stuff we don't need. To make it more complicated, I would be giving you new messages about what I wanted and didn't want about every 3 or 4 seconds. So the kidney is there picking up signals about the composition of the internal milieu and then doing whatever it has to do to get rid of some things and get other stuff back. Does this through a series of receptors that measure the dissolved solutions, blood pressure, pulse, temperature, almost everything you can think of. It's a huge and fine regulatory mechanisms. Now, what it also does is it gives us the convenience. It pools all the urine in a place where we can actually regulate when we want to take the time to stop and get rid of the urine, which is the waste product. It also has a few other secondary functions. These functions include maintaining blood volume. The kidney knows how much blood volume there is. It maintains normal blood pressure. It has sensors that are fed back to the kidney to tell us what the blood pressure is. It certainly is there for normal blood composition and normal body and blood pH. Measures that as well. It synthesizes a couple of things, the calcitrol, which is one of the calcium regulating hormones, and also something called erythropoietin. Erythropoietin synthesizes red blood cells, or increases the synthesis of red blood cells. Now, you may have come across this in a synthetic form today. For example, patients with anemia from chemotherapy or other diseases can actually take synthetic erythropoietin to stimulate their body's production of new red blood cells, something we've taken right from the body and made it our own. The words we use to refer to the kidneys that you'll hear a lot are either nephro, like nephrolithiasis is kidney stone. A nephrologist is a person who specializes in the study of the kidney, and also renal. We have the renal vein, the adrenal glands, the renal arteries. So those are two names that'll come a lot. There's no difference in what they mean. We actually use them interchangeably. Let's look at a closer look now of the kidney. This is the right kidney seen in front, and we have taken a frontal section and removed the smooth part facing us, and we're looking right at a slice down the middle of the kidney. They're very well protected, as I showed you, by both ribs and muscles. It doesn't have collateral circulation. And yet the simplicity has been kind of a gift in a way. If you look here, just outside the kidney, we have one artery, one vein, and one ureter. That was a surgical gift, because when we got ready to do kidney transplantation, technically it was very easy. First man to successfully transplant a kidney was Dr. Joseph Murray. He was a general surgeon and a plastic surgeon, and he did this at the Peter Bent Brigham Hospital in the middle of the last century, on identical twins, so there was no rejection problem. That was the first successful transplanting. But look what he had to do. He just had to sew one artery, one vein, and one ureter together, and then put the kidney in place. It also this was the place that changed our definition of death. Because once transplantation got going, we could now look at a person whose brain was dead, usually from trauma, but who had all their organs functioning. The heart might be beating normally. It didn't matter if the lungs were working, because we could put that patient on a respirator and keep the blood oxygenated. So all we needed was the body to be intact and the heart going, to keep the patient's organs well perfused until we rounded up all the recipients, because we could get 2 kidneys. That would be 2 patients. We can get a liver, we can get lungs, heart, corneas, all sorts of organs from one person who's been unfortunate enough to have brain death before the rest of the body died. This was the beginning of wanting to change that definition, which had always been the stopping of the heart. Now the new practicality took over and this is what governs when patients die at this point. Let's go back to the kidney. The kidney is composed, as other organs we have seen, of a cortex. This is the renal cortex out here, and a medulla, which is the inner section, and then something we call the renal pelvis. So you can see the medulla kind of pooches in to the renal pelvis, and this is basically the first collecting system. As the kidney squeezes out the urine through its filtration, it all collects here. Once it crosses over into this portion, it is never modified again. All the modification takes place back up here in the cortex and the medulla of the kidney, not in the pelvis. It then flows by both gravity and by peristalsis. The ureter can peristalse, and the peristalsis moves it on down into the bladder, which is low in the pelvis. And we see in most kidneys, about 10 or so medullas with what's called the papilla here. This is where it sticks in to the renal pelvis. And we can also call this a calyx. And we go from the papillary duct or the papilla into a minor calyx, combining into a major calyx, then the whole pelvis, and so on, down to the urinary bladder. Now, the place in the kidney where everything goes in, where it all enters the body of the kidney, this circle right here is called, in the singular, the hilum of the kidney. And in the plural, we actually don't refer to it very often because we're usually talking about a single hilum, or hilus is another word of the kidney. We've seen that before in the lungs, right where the two bronchi meet to go into the trachea. That's also called the hilum or the hilus of the lung. The vascular supply of the kidney is kind of interesting because it changes from outside the kidney, where we only had one on each side, and then when it gets inside the kidney, that's where we get collateral circulation, not from other vessels, but to the different segments of the kidney. So in theory and in practice, you can remove part of a kidney. If a patient had a very small tumor up here, there's enough segmental blood supply so that the rest of the kidney could survive if we took, let's say, the top half off. This wouldn't be the case if the arteries came in here, made one route through and out the vein. Then you'd have to sacrifice the whole kidney. So there is some redundancy in the blood supply. And then we have sections, they get down into small sections. This is an arcuate vein, and we have interlobar veins which go between the small inner lobes of the kidneys. But basically, the important point here is what we have is a structure that can be segmented if we need to. Moving on to the microscopic anatomy, and this is where we're going to spend almost all our time. It's the microscopic anatomy of the kidney that's most pertinent. Let me give you a big picture that's a little confusing, and then we're going to zero in on something more schematic, something that looks more real. The functioning unit of the kidney is the nephron. And this numbers approximately 1 million in each kidney. So you have an organ that's the size of my fist that will be divided into 1 million parts for each functioning unit. You are born with all the nephrons you're ever going to have. Just like the brain has most of its neurons, you have all the nephrons. You cannot make new nephrons. However, the workload can be modified. So we can take away half your nephrons by removing a kidney. The other kidney will not hypertrophy and get new nephrons. It will just increase its workload and can function perfectly well. So this is why we're able to have people give kidneys to each other. We don't have to have a dead donor. We can have a related donor or a good match, and a healthy person can remove one kidney, give it to the recipient, and still lead a perfectly normal life. Given up, however, the backup kidney. It certainly is a risk that the donor takes and certainly shouldn't be ignored. Now, what happens is, I want you to look at this big picture and see what the nephron actually is composed of and where it fits into the big picture. So if we look at the kidney again, this is about the extent of the nephron. This is its length. Certainly it's not its size and width because this is not 1/1,000,000th of the kidney. But if you see this little cup here, that's the glomerulus. And then we have what's called convoluted tubules, because they're twisty. And then the loop of Henle, more convoluted tubules, and then down through the collecting system into the calyx. We multiply this by 100, and then it looks exactly like this. So here we have this glomerulus. I'm going to get to this in great detail. Then the convoluted tubules, the loop of Henle going down into the medulla, another convoluted tubule, and finally the final collecting duct that leads to the papilla or the minor calyx and into the renal pelvis. If we now go to something that's fully schematic and not real in the sense of the way it looks in real life, but in the way it's going to function. We see the way the kidney basically operates anatomically. Next time we'll see the way it operates in detail physiologically. First of all, the renal corpuscle is here. Now this is hollow. We're looking actually at the inside of something. Here's the hole. This is the outside skin, but remember, this is all hollow. And it is in apposition to this blood vessel. And this is again simplified. This we have an afferent arteriole, a very tiny arteriole, something called the glomerulus, which means the little ball, which is where it goes in here, and then an efferent arteriole. Remember, of course, afferent means toward the target organ, efferent is away. And then we get down into these small capillaries and something called vasa recta, or straight vessels, and they are very, very close physically to the collecting system so that things can still go through them. Things we want to reabsorb can get across and go back into this very small vessel, and other things that we want to put out of the body can go into the tubule as well. It doesn't all have to happen up here. It is, again, a unique blood flow. Remember the two portal systems we had from the liver and from the brain? We have something like that here. Here's a close-up, again diagrammatically, of the afferent arteriole and the efferent arteriole, but it breaks down into tiny little capillaries. So we have an arterial capillary to capillary system that is unique here. We had venous capillaries on the other two systems. This is arterial. Look at something else. The afferent arteriole is more than twice the size of the efferent arteriole. What does that mean and why does that happen? Nature doesn't do things by accident. What it means is we're going to have much more pressure on this side because we don't have enough room to get it out the other side. We're pushing with a big piston against a little opening, and that means the pressure in here is going to be much, much higher than it is coming in. In order to get this volume out this side, we're going to have to push hard. What's happening at this point is we're trying to get everything across that layer of cells and out into the collecting system that we want out there. What we're going to do is err on the side of getting too much excreted and worry about getting it back later. That's how we're going to do this selective picking in the garbage dump. And then the other thing that's going to come back to us to haunt us is the visceral and peritoneal layers again. We have basically a meshing of the two balls, the little vessels of the arteriole and the cup of the collecting system are going to come together, and the cup side is going to be like the parietal peritoneum. And the little vessel side of the arterial system is going to be like the visceral side, and they're going to join and be intimately wrapped together, just like all the other balloons you talked about. Embryologically, this is the way it came together, and this is the way it works best all over our body. So we have this unique blood flow. We have the afferent and efferent arterioles, the afferent being the larger, producing this pressure gradient. And this ends up giving us a tubule and a collecting system that needs to do a lot of work to get stuff back that it wants. Let's go down even one more layer and look at what is a schematic drawing of an electron micrograph. This might be enlarged somewhere in the neighborhood of several hundred times the normal size. This one is probably, and this might be up to maybe 1,000 times. That's about as far as light microscopy goes. This would be an electron micrograph that might be 70,000 times its normal size. Here you have this very clear picture now of the cellular lining, the endothelium, and what we would consider the visceral peritoneum if it were in the abdominal cavity, but the visceral side of the lining against the blood vessels. And then here's the parietal layer in the glomerulus called Bowman's capsule. And as you can see, it's continuous with the cells lining the convoluted tubule, and it has micro hairs on it. Blood goes in here, and then liquids are pressed out into this cavity, where they will then float down into the convoluted tubule. Let's go back and look at this now, backing off a step. If we come here and we see the blood supply moving through here and out again, here's, looking from the other side, the convoluted tubule as it goes out and exits the glomerulus, a little ball. It's the proximal convoluted tubule, the PCT. Proximal means near the glomerulus. We're going to have a distal one here, and they're twisty for a reason. They're twisty for the same reasons we have the villi. We need more absorptive and excretory surface for there to be transport before things move along. And you can see this network of arterioles and venules surrounding the whole thing. You cut a kidney in half in a living person and the blood will just flow out because you'll be cutting literally millions of tiny vessels. Then this tubule, the proximal convoluted tubule, straightens out and it dips down toward the medulla and comes back, and the whole way it narrows and widens again. It's surrounded by all these little vessels. And these are places of exchange. This is where the body is going to use physics and chemistry to reabsorb whatever it needs and get rid of the things it doesn't need. It gets another pass near the glomerulus, so it can do some more exchange. And finally, it gets dumped out here into the collecting duct where nothing further will happen to it. It's going to drift off down into the papilla here and drop itself into the collecting system with nothing further. Now, there are some other details which we ought to look at. Let's go on and take a look at first the differences between this side. You see this very short dip? We actually have another picture that looks immediately different to the eye. These are tubules that are called juxtamedullary nephrons. These are different nephrons because they go way down deep into the medulla. They have a much longer descending and ascending loop of Henle. And the reason is these will provide further absorptive areas to do the fine tuning. It's going to give the nephron just that much more time to go down and to come back and to do the collecting that it needs to do. Now, if you move along and get a picture of what's going on here, you can see we have on this side both arterial and venous collection systems that are more normal, more what we're used to seeing. This system mimics the normal arterial venous capillary bed. Exchange there is exactly the same as it is in the normal other parts of our body, as opposed to what we just saw. Let's go back now and look at the microstructure again. We have actually photographs that would look identical to these. If you took a real electron micrograph of this, it would look exactly the same. We now have our blood flowing through this system, coming back out the efferent tubule, and under great pressure. There's a pressure to push things out here. If we get a close-up, this is the 70,000 times blow-up, we see that it's divided into three layers. First of all, there's an endothelial layer, inner lining, of cells, and it's called an endothelial fenestration, meaning windows. It's porous. It's not solid. It has tiny openings, which are relatively big, but they're still smaller than something that's wide open. And what happens in here, blood flows through here. We want to get almost everything that's not red blood cells or white blood cells to get out so we can get them into the process of sorting out what we need. These pores are big enough so that proteins and dissolved particles can get through the pores, and red blood cells can't. We don't want red blood cells to be lost in the urine. Red blood cells in the urine are a sign of disease, period. They are never normal. That disease may be in the bladder, may be from the kidney, may be from the ureters. You can get blood from kidney diseases. There are inflammations of the glomerulus called glomerulonephritis. That will put blood in the urine. You can have a kidney stone roughing up the edge of the ureter or in the renal pelvis, causing bleeding. That'll put blood in the urine. You can have cystitis, an inflammation of the bladder itself from bacteria or from other irritation. That will also put blood in the urine. But the blood in the urine tells you something is very wrong, needs further investigation, and there are other tests we then do. So we don't want blood in the urine. And mainly it's a matter of economy. We just don't want to lose our blood that way. It's too easy, it's too constant. The next layer is a basement membrane of this glomerulus, the little ball. And what it does, it prevents the large proteins from coming out. We can still get stuff across, but we can't get the big proteins because they're hard to replace too. We spent energy to build them, we need them, and if we have protein in the urine, that too, like blood, is a sign of disease. Glomerulonephritis, inflammation of this organ does it, and that dipstick that we stick in the urine, besides looking for glucose, which shouldn't be in the urine, also looks for protein, also looks for red blood cells. And with one dip, you can now find anything that may be wrong with the urine on one of these chemical sticks. Finally, there's an extraordinary system of something called podocytes, foot cells, and these are on the visceral layer of these arterioles, and they have interdigitating, I want to say fingers, but really since they're podocytes, we should say toes, that wrap around here, and each one is called a pedicel, a little foot. They wrap together and they sit on the top of the basement membrane, and they have a slit membrane. See right here, this very fine particle that attaches them together, and it prevents the passage of medium-sized particles, perhaps amino acids, smaller than the proteins, bigger than the ions. The other particles can get through, sodium ions, potassium, and so forth. And in some cases, glucose. But we don't want glucose coming out in the urine either. So this is the first place of filtration. And all the rest of this system is going to be dedicated to getting back what we lost at this point. When we get when we get liquid forced across here to the lumen of the convoluted tubule, it should be completely free of protein. It may have glucose in it at that point, but we're going to get that back. It should be completely free of red or white cells or any cellular debris. It's going to have varying amounts of sodium, potassium, chloride, bicarbonate. May have some calcium in it. Other particles that we're now going to try to get back here. And there may be toxins left in the blood that are small molecules. We'll try to get rid of those back here as well. So it's a very selective organ, and it's one that has taken us a long time to understand. The physiology of this was pioneered by a man named Homer Smith at Mount Desert Island in Maine. He studied the structures of fish. He wrote a book called From Fish to Philosopher, which makes very good reading. And he did a lot of the experiments. They dissected out some of these nephrons and discovered the anatomy and then the physiology of how this all works. Let's move on to it for a second and complete the trip through the urinary tract, and then we'll come back next time and look at the microphysiology of what goes on in this particular section, mostly in the nephron itself. If we go back to the very first slide, just to remind you of the position, we have now left the kidney and we're traveling through this conduit called the ureter. There are two ureters. They are surgically very important, and they are important in disease states. First of all, the ureters are retroperitoneal, so they're hard to see, and they cross the pelvis by going across the blood vessels here. Then they go in the wide arc of the pelvis and into the back of the bladder. They are surgically very vulnerable right here, because right here is where the base of the vessels of the colon come into play. Same thing with the right colon on this side. And it is not hard to accidentally cut the ureter. That's a surgical disaster. If you cut a ureter and don't know you've cut it, you'll be leaking urine into the abdominal cavity because you'll have made a hole into the peritoneum. You'll have a very sick and possibly dead patient. It is easy to cut. And this is the thing you spend a lot of your time, like the recurrent laryngeal nerve, when you're taking out a thyroid, you spend most of your time protecting it. A colorectal surgeon spends most of their time protecting the ureter, identifying it, knowing where it is, then putting sponges to cover it so you don't cut it. If you do cut it, the important part is to just know you've cut it so it can be repaired like any other organ. The disaster is cutting it inadvertently, putting a tie or a clip on it, thinking that it may be a vessel. It can look like a vessel. It doesn't pulsate like an artery, and it peristalsis. It moves the urine down actively from top to bottom. So in weightlessness, like in space, you'd still have active flow of urine into the bladder. That peristalsis is just like the peristalsis in the abdomen. It can cause excruciating pain. If it is stretched, like the abdomen, there will be pain, some of the worst pain that you can imagine. Let me digress now and remind you that kidney stones, though they can be up here in the renal pelvis, also can tumble down through here, and they're very irritating. They're sharp, they're rocks. They can cause the ureter to go into spasm to try to get rid of them. The ureter may try to move it on down, and as it drags and scratches the inside, it really hurts. It's considered one of the most painful things that can happen to you. There was a man named Harold Wolff, a neurologist, who spent his entire life at the Cornell Medical Center studying pain. He was a headache specialist, but he thought we should be able to quantitate pain the way we quantitate everything else. So he studied pain, and he made a scale of pain which was never adapted because it wasn't reproducible. I don't know how you tolerate pain. I don't know what you experience when you tell me something hurts. I know what I experience, and everybody's different. You have a patient, for example, with appendicitis, and you press on the abdomen. One person will say that hurts, one person will squirm, and another will scream. They've got the same disease, but we can't really interpret their perception of pain. It's very, very difficult. But there was one thing Wolff came up with. He found that there was a threshold above which all pain was the same, that the human brain could not distinguish a certain level of pain from another. Kidney stones is up in that level. Kidney stone pain gives that kind of pain where it's just about as bad as a human being can experience. And the other one of those is supposed to be the pain of labor, the pain of childbirth. The difference between the two, and I know you're going to say it's easy for you to say because you've never done this, and I haven't, the difference seems to be the perception again. In the case of the kidney stone, it's pathologic, it's frightening, you don't know when it's going to go away, there's no reward for it, and you associate it with disease and danger. In labor, you know it's going away, you know it's normal, you almost know how much and when to expect the pain, and at the end you have a great reward, you've got your baby. So that the perception of those two pains appears to be just as bad, but the emotional reaction to them is very different. And they tend to require different amounts of pain relief. There's kidney pain that no amount of morphine or narcotic will get rid of. And yet it doesn't seem to be nearly as necessary in the pains of labor, so we are told. Now, kidney stones, therefore, are really a bad disease. They come from various disorders, including, as we have seen, parathyroid disorders. However, most of them are not related to abnormalities of the parathyroid. They come from what we call idiopathic causes which we don't know exist. We have no idea where they come from, and most of these patients have repetitious kidney stones. They may get one at a time, they may get several. Some can stay in the ureter and not come down because they're too big. Fortunately, one of the things we're able to do is we can go into the bladder, coming either through the penis or the urethra in the female, and go up through the urethra in a retrograde manner, either under local or general anesthesia, thread our way into a ureter, go back up here, and we can actually retrieve stones that don't come back. We can smash them up if they're too big, and we can put little wire baskets and pull them out. That's usually done under general anesthetic. We can also remove stones here. There is an anti-reflux physiologic valve here. What happens is the ureter comes in to the bladder and then tunnels under the muscle and then comes in here on two sides, called the trigone because it's a triangle between the two ureters and the opening to the urethra. And the pressure on the bladder, when it becomes distended with urine, will close off this portion of the urethra. And urine won't reflux back up into the kidney. When it does, that's called hydronephrosis. It can be serious, it can cause infections, and severely damage the kidney, so the kidney doesn't function very well. The bladder is another organ. It's located in the midline, just behind the pubis. It has both an external sphincter and an internal sphincter. Now, just like the anus, the internal sphincter is involuntary, the external sphincter is voluntary, and you can have control over the convenience factor. Yet we all know it gets to a point where that bladder may be so distended that the internal sphincter lets go without your control, and the external sphincter actually can't hold back the urine, and the person involuntarily urinates. Also, the length of the ureter is important. Urethra. The female urethra is shorter than the male's, and this has an effect on continence. It is easier for a female to become incontinent because of the distance of the urethra than it is for the male. And there are certain disorders, including childbirth, which can put pressure on this apparatus to disrupt it and make the patient incontinent. Let's say one word about dialysis. We touched on it briefly in one of the early lectures. One of the things we can do for a patient who does not have any kidney function or markedly decreased kidney function is that we can set up an artificial kidney. We have a membrane that can mimic the glomerulus. So we can take blood out of the patient's artery or out of the patient's vein. It doesn't matter. We can run it through a pump that brings it into a machine that has a semi-permeable membrane, a membrane like the collecting system in our kidney, and we can make this solution exactly the way we want it. We take a solution of water, we put in salt, potassium, chloride, everything we want on the body side of the patient eventually, we put it in on the dialysis side. And then, because this is an osmotic membrane, the flow of the blood will go past it and the sides will equalize. So if you don't have the right amount of sodium in your blood, it'll equalize with the sodium we've put into the solution, and the potassium and the calcium. We can make the blood any way we want it. We have the perfect situation on the outside of the membrane, and the blood will then reestablish the perfect situation on the inside of the membrane. Because there's lots of waste on the inside and nothing on the outside, we don't put urea in there or ammonia, that'll all go out. And then if we have too much sodium on the outside or a normal amount and not enough on the inside, some will come back. It will quickly equilibrate. And it will make it perfect in a very short pass. And then we go back up into the body. And this goes on for several hours. This membrane actually doesn't even have to be sterile, because bacteria don't go across the membrane at all. It can be an open bath. It used to be like a big wash tub. Now they've gotten smaller, a little more elegant, but the principle is the same. We use osmosis, which I'm going to explain later, and a semi-permeable membrane that allows some molecules and not others to go across. Again, like in the glomerulus, the blood won't go out, so we won't lose any blood or protein, but we can balance the blood. This is done about every 2 to 3 days for these patients. It's done as an outpatient. Some of them who are ill have it done at home. And They get along very well. This can carry a patient without kidneys for long periods of time until either they get their transplant or until they die of other disease. It's expensive, but it's an elegant way of treating this disease. Next time we'll move on and we'll look very carefully at the actual physiology of what happens inside the nephron.